Swayam Prabha. Digital India. Educated India.
Let us start our today's lecture on this video course of Geotechnical Earthquake Engineering. Let us look at the slide here. On this video course of Geotechnical Earthquake Engineering for NPTEL, we are going through this module 4 on strong ground motion. Let us do a quick recap what we have learned in our previous lecture. Like we have learned about what are the amplitude parameters of an earthquake, like it can be acceleration, velocity and displacement record with respect to time. Then how to define the peak value of the acceleration, we have seen that PHA, peak horizontal acceleration, and it can have two orthogonal components in north south direction and east west direction, and the maximum resultant value of that PHA we can take by taking the vector sum of those two orthogonal PHA values. And Trifonink and Brady in 1975, they have proposed for the design what is the value of PHA with respect to the relationship with the modified Mercalli intensity scale, MMI scale. And generally the PVA is not that important. Earlier people used to think about, like as proposed by Newmark and Hall in 1982, but in recent days people say it is better to estimate PVA also, that is peak vertical acceleration, and in absence of the data of PVA, as per suggestion by Newmark and Hall 1982, PVA can be considered as 2/3 of the value of that PHA for the design purpose. And peak acceleration data with frequency content and duration is more important, because we have seen that it is not necessary that only that PHA value will be more important. It is also necessary how much is the frequency content and how much is the duration of an earthquake. Then we have seen that relationship between PHA versus MMI and PVA versus MMI. So, this is for the vertical, this is for the horizontal as proposed by Trifonink and Brady in 1975, corresponding to various modified Mercalli intensity scale. So, if you know the MMI value of a particular earthquake at a site, using this relationship you can get your value of PHA or PVA, which can be further used for the design. Then we talked about the value of PHV, that is peak horizontal velocity, and we have mentioned that PHV is a better estimation than PHA because of capturing the intermediate frequency also very well, but whereas the peak displacement or peak horizontal displacement and peak vertical displacement, though they are associated with the low frequency content, but because of the filtering error, that is after filtering out the noises etc., it will be very difficult to get a reliable results in terms of your peak displacement values. So, that is why in most of our earthquake engineering design, either we use PHA, that is peak horizontal acceleration, or PHV, peak vertical acceleration. Then we talked about various other amplitude parameters like sustained maximum acceleration. We have seen it can be a 3 cycle sustained or 5 cycle sustained, depending on your requirement, that is how much that highest value of acceleration is continuing through how many numbers of cycles. Then we have seen for the design what is known as effective design acceleration, and as per the proposal by Kennedy in 1980, that EDA can be considered as 1.25 times of that 3 cycle sustained maximum acceleration of PHA, and Benjamin and associates proposed that if you filter out all the higher frequencies, that is above 9 hertz frequency, if you filter out all accelerations, then whatever acceleration spectra or acceleration response you get with respect to time, that acceleration time history, whatever PHA value it gives, directly you can use that as your design or effective design acceleration. Then to provide the frequency content parameter, we have seen either using Fourier spectra or by power spectra or by response spectra, we can find out how much frequency content exists in a particular earthquake motion. Fourier spectra is nothing but it is an assumed Fourier series of a randomly behaved earthquake motion that we express in the form of a Fourier series through this periodic function, and this value is given as the amplitude and this value is given as the phase angle of whether if you consider it as acceleration or displacement, accordingly this value will correspond to that value of amplitude and phase. We have seen what is known as Fourier amplitude spectra, which is nothing but a plot of that amplitude versus frequency, and also we have seen Fourier phase spectra, which is nothing but a plot of phase versus frequency. This is a typical plot of Fourier amplitude spectra, Fourier amplitude in log scale in y axis and frequency in the log scale in the x axis. There we have found what is the definition of the corner frequency and the cutoff frequency, that is the minimum value of the frequency at which that maximum amplitude or maximum value of that Fourier displacement or acceleration, whatever you take as a response, that will start, and cutoff frequency is up to that maximum frequency with up to which it will continue. Then we have seen another mathematical expression of this earthquake motion through power spectra. The advantage of this we have discussed, that it can consider the random process through using this power spectrum density function like this. Then we have discussed the most widely used frequency content parameter through the response spectra. As we have mentioned, response spectra can be a acceleration response spectra or displacement response spectra or velocity response spectra, that we have seen for various rocky site and soil site acceleration, velocity and displacement response spectra. How this response spectra is obtained? Through the single degree of freedom mass spring dashpot model by applying an particular input motion corresponding to a particular exciting frequency and the damping ratio. So, we will derive it today in this lecture. Also, we have discussed about the duration. In the duration, we have seen it is nothing but the time required to release the entire strain energy during an earthquake process, whereas the relative duration is nothing but it is the time between that 5% to 95% release of the energy. And for engineering design, we have seen another important duration parameter is nothing but bracketed duration, which considers the time duration where earthquake acceleration is more than that minimum value or threshold value of acceleration, which causes damage to structure, which is 0.05 g. So, that is the time or duration which is known as the bracketed duration. With this, we had completed our previous lecture. Now, we will continue our today's lecture with the derivation of the response spectra. So, let us go back. This is the typical picture of a response spectra. How to arrive at the response spectra, because this is the maximum used frequency content parameter in the earthquake engineering. Let us take a simple mass spring dashpot single degree of freedom model, which we have already discussed in our previous video course on soil dynamics, but for clarity let us complete it once again over here. Let us say this is a single degree of freedom system, as we know is DOF system with mass m and spring constant k, and ut is nothing but that single degree of freedom which defines its position at any instant of time, and pt is nothing but the externally applied dynamic load on the system. Suppose if we have the variation of this pt with respect to time. So, how this pt varies with respect to time? Let us say it varies like this. Let us take a very simple example first, then we can idealize it to a generalized case. Say this is the dynamic load which is acting on the system, that is from time 0 to time t d, it is a constant force which is acting on the system is P naught. After t d, there is no force acting on the system. What does it mean? From time 0 to t d, it is a forced vibration, and beyond time t d, it is a free vibration case. So, that is the simple problem which already we have discussed in soil dynamics. So, let us see the solution of it. For that, we should have the initial conditions be known, because that is the basic information should be known to us. Let us say u, that is displacement at t equals to 0, say it is 0, and u dot at t equals to 0, that is the velocity at time t equals to 0, let us say that is also 0. That is, I am considering a system which is starting from absolute stationary condition with 0 displacement and 0 velocity at the initial starting of the dynamic time t. Okay. Now, as we have already identified, it is having two phases of vibration. One is forced vibration case up to time t d, and then the free vibration case beyond time t d. Let us see how the variation is occurring. So, let us consider for different portion, that is for forced vibration phase, that means t any time should be less than or equals to that t d, because force is acting till the time t d. So, any time if we consider between this range, that is nothing but a forced vibration phase. So, what is the solution of this one? If we refer to our former course on this soil dynamics, we will see that u of t with u s t, u s t is nothing but static value of the displacement, can be expressed as 1 minus cosine omega n t for a constant force like P naught is acting on the system. Okay. So, that was the solution already we have derived in our soil dynamics video course. If you have gone through that, you can easily understand. I am not again repeating that portion, I am trying to derive beyond that what is the response spectra. So, if you are having any doubt, you can refer to that course and clarify by yourself. In this case, omega n is the natural frequency of the system, which is nothing but root over k by m, which is nothing but once again 2 pi by T n. T n is the natural time period. So, if I express it in terms of T n, it will look like 1 minus cosine of 2 pi t by T n, and this is valid, as I said, for a time which is between 0 to T d. So, this is one set of solution as we already know about it. Okay. So, now let us see what will be the response in the free vibration phase. So, in the second phase, that is for free vibration phase, that means the time exceeds that value of that T d, right. That is nothing but a free vibration, because you have taken out the load. What is your equation of motion? You have basic equation of motion mu double dot plus k u equals to 0 from our chosen model. Now, u of t, the solution of that t equals to, can be written as u at t equals to T d times cosine of omega n t minus T d. That is the initial displacement for this case of free vibration. What is the initial displacement for this free vibration? That is the last point of the previous phase or forced vibration phase. At t equals to T d is the nothing but the starting point of your free vibration. Okay? Plus the velocity u dot at t equals to T d by omega n times sine of omega n t minus T d. That is the solution, as we know, for any free vibration phase, that initial displacement times cosine of omega n t plus initial velocity by omega n sine of omega n t. In this case, t is nothing but beyond that time T d. So, that is why t has been replaced by t minus T d, and the initial time has been taken as where the t equals to T d condition was existing. So, at t equals to T d, it is the starting time for the free vibration. That is the reason, as I have already mentioned, starting time for free vibration phase. Now, with this, what we can rewrite this as a solution, let us see over here. So, next we can write that u at t equals to T d will be equals to u of s t 1 minus cosine 2 pi T d by T n. This is the solution we can write from the forced vibration phase, because that was the solution we have seen, u of t by u of s t equals to 1 minus cosine 2 pi t by T n. So, I have just placed t equals to T d over there. So, that is the initial condition, and initial velocity u dot should be for this second phase of free vibration can be u of s t. If I differentiate this, omega n sine of omega n T d. Okay. Fine. Therefore, what we can write, u of t by u of s t static can be written as, the initial value is 1 minus cosine of 2 pi T d by T n times cosine of omega n t minus T d. I am writing now the complete solution, that u of t for the second phase, that is the free vibration phase. I have taken this u s t out in the denominator, that is why we can write it like this, plus sine of omega n T d times sine of omega n t minus T d. Okay? Because omega n was in the denominator, so it gets cancelled. So, remaining portion is this one, I have already taken this out. So, this is the simplified form. Am I right? Therefore, if I further simplify it, I can write it, u of t by this u of s t can be written as, this is a trigonometric function, as you can see the variation. We can simplify it and rewrite it as 2 of sine pi T d by T n times sine of 2 pi times t by T n minus half of T d by T n. So, this complete solution for the second phase is valid for which time? So, this is valid for t greater than equals to T d. Am I right? So, what we can see in this case, that if you look at the value or the function of that u t by u s t, it is a function of this T d by T n ratio. That is why I have expressed it in this form, T by Tn ratio and Td by Tn ratio. Is it clear what I am trying to say? Let me express it in a more simplistic way. Therefore, my final output says that u of t by u of st, that is the dynamic displacement with respect to the static displacement, is a function of what parameters? That Td by Tn ratio and that T by Tn ratio. So, that means any dynamic response or dynamic displacement is dependent on not the individual values of this duration up to which the earthquake is acting or the dynamic load is acting, nor it is dependent on the individual value of the total duration or the individual value of the natural time period of the system, but it is dependent on the ratio of this, that is how long the dynamic load was acting over the natural period and how long the total time you are considering. What does it mean? Suppose earthquake duration was for say 20 seconds, and I am interested that after 1 hour of earthquake what is the damage on my structure. Then this function tells us clearly that in that case in the solution you have to put Td as your 20 seconds, but T has to be 1 hour. Okay? That is 3600 second. Clear? So, it is clear that the damage we are considering for any structure, whether substructure or superstructure, anything, it is not only a function of your earthquake duration, it is a function of your at time where you are interested to, but not that individual value, it is related to a ratio of that natural time period of the system. Clear? That is the reason, if you look, if you have understood this solution clearly, this automatically tells us that it is not necessarily that all the earthquake damages are going to occur during the earthquake or soon after the earthquake. It may happen that your structural damage or any damage as such due to the earthquake in the soil also may occur after a large time has spent after the stopping of the earthquake also. So, that is what I wanted to show through this solution. What it says? It says the dynamic displacement or the response is not only a function of that ratio of duration of earthquake to the natural period, but it is also a dependent parameter on at what time you are interested to know the behavior of your structure. Okay? So, we have to be careful about both these two parameters, this as well as this ratio. So, once knowing that, let us find out what is the maximum response, then we can probably be able to appreciate it. Maximum response of the structure subjected to this case. So, in the forced vibration phase, that is the first phase, forced vibration phase, if we look at T equals to Tn by 2, that means, if our time is equals to Tn by 2, then what will be the value of that ut by ust maximum value, maximum amplitude of that will be equals to 2. Am I right? That is, if you put it in this solution, I will show you once again, that is what was my solution for this case. If I bring it here, yes, this was the solution. If you look at here, within the forced vibration phase. So, I am talking about within forced vibration phase. So, obvious reason is my T has to be within Td, Now, what I have chosen, this t value I have chosen as T n by 2, that is the ratio I have taken as T by T n ratio I have taken as half, 0.5, right. So, if it is so, if you put that value, what it is becoming? It is becoming minus of cos pi, so plus 1, so 1 plus 1, 2, that is the possible maximum value of this solution, right. So, that is why I have said it gives us the maximum value of this u t by u s t max is 2 at this point. Now, if your value of this T d is greater than this T n by 2, then what happens? Then we have to see two solutions. What are those? We will look at here. So, let us mention this as a response. Let us identify this as a response u t by u s t, that is with respect to static. So, if I want to show the response R d, let us say response, which is nothing but u t by u of s t I am defining. It can be expressed by two solutions, 1 minus cosine of 2 pi T d by T n and 2. These are the maximum values. This is applicable when your T d by T n ratio is less than equals to half, and this is applicable when T d by T n ratio is greater than equals to half. Am I right? So, that is what we said just now, that maximum response is very much dependent on this ratio, as you can see. If this ratio is less than equals to half, then your maximum response will be computed like this, based on whatever value of cos you are getting, that will be coming. But if this ratio is more than or equals to 0.5, in that case always your maximum response will be 2 times. That is, the dynamic response will be 2 times of your static. Clear? Now, let us see in the another phase, that is the free vibration phase. So, for second phase, that is for free vibration phase, what is the maximum value of this u t? So, if I write down that u t of max, that will be nothing but your amplitude, whatever you are getting at t equals to T d, that square plus that u dot t equals to T d by omega n, that one square. Am I right? Are you satisfied with this expression? Let us look at here. So, as I said, the solution of this will be in the form of, for free vibration phase, I brought it this here, u of t is expressed as initial displacement times cosine of omega n t plus initial velocity by omega n times sine of this. So, what can be the maximum value of this u t? Obviously, it will be root over this amplitude square plus this amplitude square, right. So, that is why u initial square plus this velocity by omega n, this square, that will give us the maximum value of this entire solution, is not it. So, u of t maximum, that is why I said, can be written as this. Now, if I simplify it, so u of t, this max, u of t max can be written as, on simplification, by putting the known expression 2 of u s t times mod of sine pi T d by T n. Where from I got it? Let us look at the solution of this, then we will able to understand. Yes, here was the solution. If you remember this one, If you see, this was the solution for free vibration phase at the end, right. So, what is the maximum value of this solution? This portion, this amplitude remaining is sine. So, if sine is 1, then it will be maximum. Am I right? So, if it is maximum, so 2 times UST sine of pi Td by Tn, that is what I have written over here, and it can be amplitude either minus or plus. So, with this absolute response will be, let me write it down once again. So, therefore, the absolute maximum response, that is R d what we are expressing, that can be written as 2 times of that sine pi Td by Tn. This is for the free vibration phase. Therefore, if I write it in a combined form, I can write it as 2 times mod sine pi Td by Tn, 2 solutions actually. This is one case, another case is 2. When this case is valid, when this Td by Tn ratio is less than equals to half, and this condition when Td by Tn ratio is greater than equals to half. Is it clear? See, this is the complete solution. What is the maximum value of this again? When this sine parameter is 1. Am I right? That will give us that value of 2, maximum value. When it will occur? That will occur when this ratio Td by Tn is more than equals to half, right. Otherwise, if it is less than equals to half, it has to be 2 times of whatever the sine value gives us. So, this is the response in free vibration zone, and in the forced vibration zone, if you look at, this was the maximum response. So, everywhere it is a function of that Td by Tn, and the T by n concept will come to you only when you are interested about a particular time when you want to study the effect on your structure. As I said, after 1 hour, after 30 minutes, after 10 minutes, like that. So, that is the reason, if you see over here, here I have not considered the damping portion, but if you consider the damping portion, if you remember my soil dynamics lectures, the typical value of this plot, the response spectra, which we show that Tn and say Sa by G, it can be acceleration response spectra, it can be displacement response spectra, it can be velocity response spectra. This looks like this for a particular value of your damping ratio, say 5% damping or something like that. For a particular damping ratio, this behavior we can obtain. Okay? And if I want to plot this ut max by S for our case, how it should look like, let us see. So, I am now plotting this value of u r d versus T d by T n. So, this is the variation of T d by T n with respect to R d. R d as I have defined. So, u t by u s t, maximum of that I am plotting. So, as I said over there, it is 0. So, this is 1. So, this is 2, this is 0, let us say this is half, this is 1, then this is 2, then this is 3, like that. So, at half, if I draw over here, the variation will be something like this. Okay. So, maximum response it occurs at the Td by Tn ratio of this one, when it is subjected to a that constant force type vibration for a finite time period. But if it is a random, similar process has to be used to get the solution and get this response like this. So, that similar procedure we adopt for the earthquake random motions also, which probably you have to solve using the Duhamel's integral process, which I have discussed thoroughly in the soil dynamics course, right, for any kind of motion. But everything finally will be a function of this, how long it is occurring, that earthquake motion with respect to the natural time period, and at what point of time you are interested to find out the value or response. Okay. So, another parameter I want to highlight over here, let us look at here, like it is called the pseudo value of acceleration response spectra and pseudo velocity response spectra and pseudo displacement, how it is defined. Let us say this is a typical structure of height h, which is subjected to this force Fst over here. I have a base shear here V naught t, let us say, and a moment, resisting moment, let us say m naught t for this structure, and let us denote that u naught as the maximum value of that u of t, the function, which whatever it is subjected to any kind of dynamic load. That Fst is nothing but a spring force acting on the structure with k as the spring constant or the stiffness times u of t, which if we simplify it further, it can be expressed as m omega n square times u of t. Why? Because as we know omega n is nothing but root over k by m. So, automatically k is nothing but m omega n square, is not it? So, in this case we call it as m times a of t. What is then a of t? If you look at here, a of t is nothing but, as per our written expression, a of t is omega n square times u of t. So, this a of t is known as pseudo displacement. So, this is pseudo displacement this a of t. So, a of t can be written as omega n square u of t. This a of t is called pseudo acceleration. Pseudo acceleration response spectra. So, this is a, if we plot this value of u naught, what is u naught? As I said, it is a u t max. If you plot this u naught versus this T n, that is known as displacement response spectrum. And if you differentiate it further, this u naught with respect to time, what you get over here, that u naught dot, which is nothing but maximum of this u dot t versus the T n, that plot will give us velocity response spectra. If you further differentiate it with respect to time, u naught double dot is nothing but maximum of this u double dot t versus the plot of T n, that gives us the acceleration response spectra. So, for the chosen solution of A of t, what we have seen. So, pseudo velocity response spectra can be obtained as, let us say v, in the unit will be velocity unit, say meter per second, will be omega n times d or omega n times displacement 2 pi by T n times d, and pseudo acceleration response spectra will be A in terms of meter per second square unit, that will be omega n square times this d. D is pseudo displacement. So, what I have written over here earlier, if I correlate, you can see over here, this is known as pseudo acceleration, which is nothing but omega n square natural frequency square times your velocity, your displacement profile with respect to time, omega n square times u of t, right. So, that will give you the pseudo acceleration response spectra. So, like that we can draw any response spectra, whether it is a pseudo acceleration response spectra, pseudo velocity response spectra, or pseudo displacement response spectra. Now, let us come back to our topic. Now, let us start some more parameters like other spectral parameters. What are the others? Various spectral parameters which generally are used. One is called RMS acceleration, nothing but root mean square acceleration. So, this is the parameter that includes the effects of amplitude as well as frequency. So, this acceleration parameter root mean square acceleration, it considered the both effect of the amplitude as well as the frequency. It is expressed in this form, A of RMS equals to root over 1 by T d integrate 0 to T d A of t whole square times d t. A of t is nothing but your actual variation of acceleration with respect to time. If you integrate over the time period that T d and then find out the root mean square, this is nothing but the, you are taking the mean by dividing it and root you are taking. So, root mean square acceleration you will get by this over the time domain, and T d is the duration of the strong motion. Okay. And A I is another important spectral parameter which are commonly used for design. A I is nothing but full form is areas intensity. This areas intensity is a measure of the total energy at the recording station and is proportional to the sum of the squared acceleration. So, it is defined as areas intensity is pi by 2 g integrate 0 to infinity A of t whole square dt. So, that acceleration response with respect to time, whatever you have during an earthquake, if you integrate it over 0 to infinity by taking a square of that and then multiply it by pi by 2 g, that estimate the total energy which is measured during a recording station, which is known as areas intensity. Another spectral parameter is spectrum intensity or SI. SI is defined as the integral of the pseudo spectral velocity curve. Just now I have discussed what is pseudo spectral velocity curve, which is known as the velocity response spectra. So, if you integrate that between that time period, that is, if you have that plot of pseudo velocity spectrum versus Tn, between 0.1 to 2.5 seconds, between that whatever you get, if you integrate that curve, these quantities are motivated by the need to examine the response of structure to ground motion, as many structures have fundamental periods between 0.1 to 2.5 seconds. That is the reason why the spectrum intensity, it is calculated for any structural damping ratio to determine their response or determine their damages. Is it clear? So, this is the typical range of the fundamental period of any structure of our civil engineering structure. It will be within 0.1 second to 2.5 seconds. Clear? And in the reverse way, we can see, considering the structural period or fundamental period of a structure, if you take the in hertz, how much it is coming? About 1 by 0.1, so 10 hertz, right? And this is 1 by 2.5. So, it will be inverse of 2.5, that much hertz will be the typical range of the natural or fundamental frequency of the system. So, if your earthquake frequency also comes within that, then there you have to take care of the structural damages, etc. That is the reason you have to integrate that velocity, pseudo velocity response spectra curve between this time period of 0.1 to 2.5. Another spectral parameter is dominant frequency of ground motion, FD. What is FD? It is defined as the frequency corresponding to the peak value in the amplitude spectrum. That is, whatever amplitude spectrum you have, in that whatever is the frequency which corresponding to its highest value or peak value, that will be your dominant frequency. Thus, FD indicates the frequency for which the ground motion has the most energy, because it is giving you the maximum amplitude. The amplitude spectrum has to be smoothened before determining the FD, which is quite obvious, as we have already understand. We have to smoothen it, filtering it, etc. Other parameters like predominant period. What is predominant period or TP? Period of vibration corresponding to the maximum value of the Fourier amplitude spectrum. That is, you have to express the amplitude response in terms of Fourier series. So, as we have already seen, Fourier amplitude versus the period, if you plot it like this, the something it will like look like this. This is for two different ground motion. This is for ground motion 1, this is for ground motion 2. Can you see? For both of them, the predominant period is same, TP is same, that is where it is occurring the maximum value of the Fourier amplitude. So, this parameter represents the frequency content of the motion. The predominant period for two different ground motions with different frequency content can be same, making the estimation of frequency content very crude. That means, suppose for this one, if you plot it in the logarithmic scale, whatever is your frequency content, and if you plot this in logarithmic scale, whatever is the frequency content, they are quite different. But their predominant period where the maximum value occurs is same. That is what you have to use the combinations of these various spectral parameters to identify the nature of any earthquake motion, not only in terms of maximum amplitude, but also in terms of frequency content. What is bandwidth? Bandwidth or BW is of the dominant frequency measured where the amplitude falls to 0.707, which is nothing but 1 by root 2 of the amplitude of the dominant frequency. Again, this is based on the smoothed amplitude spectrum. Central frequency. What is central frequency? It is a power spectral density function, that PSD, what we have already discussed. Within that can be used to estimate the central frequency of the ground motion. The nth central moment and the central frequency can be estimated like this. This lambda n is the nth frequency. Okay? That can be estimated as 0 to omega n, omega to the power n, g of omega, that is the power spectral density function, times dW. and that central frequency is defined as this second one spectral moment divided by the 0th one, that is lambda 2 by lambda naught, root of that will give you the central frequency. This is another just estimate of a spectral parameter. So, central frequency is used to calculate the theoretical median peak acceleration using this expression. So, this value of this omega, capital omega, you can use further to calculate the U max value in this fashion. And the Sheff factor, it is indicating the dispersion of the power spectral density function, that PSD, about that central frequency, how it varies with respect to that central frequency, that delta can be obtained using this expression, that is the lambda 1, the first spectral moment square divided by 0th one and the second one. Then it lies between the value of 0 and 1. Higher value indicates the larger amount of bandwidth, or higher value of the spectral. Another very important spectral parameter is nothing but Vmax by Amax ratio. This is important. What is Vmax? Vmax is the maximum velocity if you consider the simple harmonic motion is applied to a single degree of freedom system like structure. What I have already discussed about the derivation, etc. And Amax is the corresponding maximum amplitude, that is from your u t max, if you find out the velocity max for a simple harmonic motion, it will be how much? Omega times ut, right? Isn't it? That is, if I want to express, suppose my u of t is having some expression, say u sine of say omega times t, then u t maximum of that is nothing but u. Then what is the V max? V max is nothing but omega times u mod of that. Am I right? Because velocity you can find out by differentiating it with respect to time, this displacement, and maximum value of that will be, this will become cosine, omega will come over here. So, omega times that u, and what will be your A max? Omega square times u mod of that. Am I right? So, that says in this slide whatever I have discussed just now, look at here. So, Vmax by Amax ratio is related to the frequency content of the motion for simple harmonic motion with a period t. This Vmax by Amax can be represented as t by 2 pi, is not it? If I look at here, let us see here. So, Vmax by Amax for this simple harmonic motion will be nothing but how much? Vmax by Amax will be 1 by omega, which is nothing but t by 2 pi, right. That is what it is shown over here. You can see here in the slide, Vmax by Amax is nothing but t by 2 pi. Now, Seed and Idris in 1982 proposed average values of that Vmax by Amax for different sites within 50 kilometer of the source. That is, they have analyzed the values of Vmax by Amax between the earthquake epicenter to a point of site of response for different types of site, that is rocky site, soil site, etc. And what are the typical values they have mentioned, the average values? For rock, they have mentioned this value of Vmax by Amax ratio. And remember, what will be the unit of this? It will be the unit of this t, that is in second, is not it? So, that is why for rocky site, they have mentioned the typical value is 0.056 second. For steep soil within the 200 feet, that is a steep soil available at relatively shallower depth, the value is 0.112 second, and deep steep soil, that is the steep soil is available beyond 200 feet. In that case, the value of this t by 2 pi or Vmax by Amax ratio is 0.138 seconds. So, what we can see, this value of Vmax by Amax ratio keep on increasing if we go from a stiffer to a softer soil. That is what it means, right. So, this gives us a very good estimation, but remember these are the typical average value. The actual value can differ, and how this value can be used to estimate for estimation of the magnitude of another location or computation of epicentral distance, that we will see through an example problem in the next class. So, with this we have come to the end of today's lecture. We will continue further in the next lecture.